Does a double integral compute? Does a double integral compute? Talked about this many times. Hopefully we got this down. You ready to start, John? Hey, John, you ready to start? Hey, John, what's up? Is that Coord tasting pretty good? Mint flavored, fruity. John. John. How's that Coord tasting?
Good.
Is it good? Okay. All right, so what does it compute? And all the details, right? So just a 2 or 3 word phrase isn't enough. Be specific. So explain all the details. So if we had that, what would it compute? Tell the person next to you. All the details. 2 or 3 words doesn't do it.
Oh, no.
Okay, so this thing that it computes, does it have to do with area or volume? Does it have to do with area or volume? Okay, is it volume? Kind of. Yeah, good, kind of. What is it? So it's, what do we call it? Net volume, we could call it. What else could we call it? Sign volume is another way to call it. Yeah. Anything else? Difference of volumes. That's what, and what are these? So by these, what we mean is difference of volumes. How is it difference of volumes? What volume minus what volume? Trinity? Okay.
I was almost there.
All right, okay. Is there another hand back there? Yeah.
It's all of the volumes over all of the points in the 2D region E.
But how is it difference of volumes? Like when we say difference, we mean something minus something, right? Yeah, Ryan.
It's the volume above the XY plane minus the volume below the XY plane.
All right, or all the volumes above the XY plane minus all the volumes below. Okay, but that's, yeah, so you kind of had it. Okay. All right, so now be specific. What volumes are we talking about above or below? Like defined by what, right? So these are solids. We got solids, right? We got solids. There might be some above. There may be some below the XY plane. Defined by what? Okay, so how does the function help define these volumes?
Well, the D is like the area, the 2D region, and then the function gives you like almost the height of it.
Okay.
Height's not like the best term, but
Function is kind of like the height of it. Anyone else? Give it a stab. What does the function have to do with this? These volumes, these solids that we're taking the difference of, and what does D have to do with it? Okay, so yeah, D is like a region in the XY plane, and that defines laterally, right? It's the lateral boundary. We extend that up and down. So it's like it defines the sides of it, right? Because D gets extended up and down like a cylinder. So D defines the vertical sides. And then what does F define? How does F come into it? He said it's kind of like the height. Is it kind of like the height? Yeah.
It's like the surface of.
The surface, okay. But then what is it? What is that surface? How does that help create these solids that we're getting the difference of volumes of?
It's like the area between that and the surface.
Okay, so the surface is like the top if it's positive, or the bottom, right? The xy plane is also important, right? That's part of it. Like, so if it's always positive, then the xy plane becomes the bottom, and the surface becomes the top. If f is always negative, then it's like the xy plane is always the top, and the surface is the bottom. And then if it switches, then it switches, right? So fxy defines what? The top and or bottom. But then the xy plane is important too. The xy plane defines the top and or bottom. Just depending on what f is, right? So depending on the values of f, whether it's positive or negative, tells us if it's the top or the bottom of this solid, and then whether the xy plane is the top or bottom of the solid. So it's net volume, but it's there's a lot more to it than that, right? So you have to have a good image of that. Okay, so can we make a double integral give us the area, give us an area? And how can the double integral give us area? Yeah, Andrew.
If f is equal to 1.
Right, if f is 1, if f equals 1, then we're talking about the plane z equals 1. And so what? It still finds a volume of a solid, right? It still finds the volume of a solid. It's just that the volume of that solid is the same value as the area of what? D, right? So if f of xy equals 1, then that double integral, it's still finding a volume units-wise, but that value of that volume is the same as the value of the area of D. So now, this whole discussion, how is it analogous now to triple integrals? So if we take this whole same discussion and so we have a solid E. So before we were integrating over a region D, now we're integrating over a solid E. We're integrating this function of 3 variables over a solid E. And so what does that find? So what does that compute? Yeah, so like net 4-dimensional volume. So we call hypervolume. Or the difference of these volumes in 4 dimensions. Okay? And so then what if fxy is 1? Then what will it do? If xyz. If fxyz is 1, if we integrate 1, then what does it compute? Just like if we were talking about if f was 1 here. Right, then we're going to get the volume of what? Just like we get the area of the thing we're integrating over, now we're going to get the volume of the thing we're integrating over. Volume of E. And that's an R3, right? So this thing that we're integrating over now lives in R3. We can draw those, we can understand those pretty easy, you know, those make sense to us. Okay, so do you see how everything's the analogy of an R3 to an R2, or like you're just stepping everything up one dimension. So if we integrate 1, that's going to get like the size of this thing we're integrating over. In this case, the area of D. In this case, the volume of E. Okay, any questions on that? So there can be problems where they're asking you to find volumes with a double integral, right? So that's going to involve a certain function, right? There's going to be problems where they're asking you to find an area with a double integral. That's your cue to know that this function should be 1. There's going to be problems in triple integrals where they'll just say evaluate the triple integral and you'll have some function here, right? So something with xy's and z's in that. But they may ask you to find a volume in R3 using a triple integral. Then what do?
Function value 1.
F is 1, right? F is 1. Okay. So that is like your problem due tonight, number 4, I think. So we're working on triple integrals, and it says find the volume enclosed by these two paraboloids. And we want to use a triple integral to do that. So these are geometry problems. We're just going to figure out what that solid E is. And then it's all about the limits, so we're going to integrate what? So this solid enclosed by the paraboloids, that's our E. And then what will we integrate? What function? 1, right? So then you're going to sketch this solid, think about what makes sense. And you can do it any way you want now. So you can use type A, type B, type C, and then your double integral, your outside double integral, you can do type 1, type 2, polar, whatever makes sense. Whatever's the most efficient. So we're going to draw it and then go from there to see what's going to be the most efficient way to solve it with all these different types of triple integrals that we can set up. Any questions on that? Okay, so we want to talk about something called cylindrical coordinates, which is, it's barely anything new. Once we see it, there's really hardly anything new to it, but it's cylindrical coordinates is an R3 coordinate system. It's just different than using X, Y, and Z. So instead of X, Y, and Z, are theta and Z. So why isn't this new? Because this is basically like using polar coordinates in the xy plane and then keeping the z variable the same. So we've done that already, right? We've worked a lot with polar coordinates so far. We've seen polar double integrals. Add the z coordinate and you have this thing called cylindrical coordinates. Okay, so just to review it, or just to emphasize, so R is first, and that's going to be what? R is going to be the horizontal distance from the z-axis. So now so you think about R isn't just in the xy plane anymore because z can be different. So R is going to be the horizontal distance from the z-axis. Okay, theta. So here I'm showing it, just look in the xy plane down there. I'm showing r distance from the z-axis. Theta, standard trig angle, once again, right? You see that at the bottom of the screen? So our standard trig angle is theta. What? Angle swept counterclockwise from the x-axis. And then z is our standard up and down from the xy plane. So this is now so once you have an r and you have a theta and you have a z, that gives you a distinct point in space. So r is distance from the z-axis, theta standard trig angle, z how high you are up and down from the xy plane, gives you a point. In my experiences, we don't have to worry about negative angles or angles greater than 2 pi. That in cylindrical coordinates, we restrict theta from 0 to 2 pi. So we're not worrying about going the other way or going around lots of ways. So that we just keep it between 0 and 2 pi. So it's just basically taking polar coordinates along with a third coordinate z, and that generating all points in space with those three rather than x, y, and z. So then you have all your same relationships. What is x? So if we're transferring back and forth between Cartesian and it's the same, right? R cosine theta, R sine theta, z is still z. Same z. And then r equals square root of x squared plus y squared, or r squared equals x squared plus y squared. Theta equals arctan of y over x, but what you got to be careful. You have to make the right adjustment for second, third, and fourth quadrants. Because arctangent will always give you an angle between negative pi over 2 and pi over 2. So you have to adjust accordingly. Adding 2 pi, or adding pi, subtracting from 2 pi, whatever you need to do to get the right angle the correct angle between 0 and 2 pi. Because arctangent will always give an angle between negative pi over 2 and pi over 2. Okay, any questions? So like I said, it's not really anything really new. So let's work on this. So I want you to practice, plot the points, 2 pi over 4, 1, 1 pi 3, 3, 7 pi over 4, negative 1. And then sketch these. What would this sketch of r equals 4 be? Z equals 2, theta equals 5 pi over 6. So I'm going to take attendance. I'm just practicing with the basics of the coordinates. Plot those points. Sketch these sets of points, right? These are sets of points. Sketch what those would mean. Go. Okay, so this is what I'm showing here, something like 2 pi over 4, 1. Maybe it should be lower. Let's do this. There we go. That's something like 2 pi over 4, 1. Agree? Sense? So we're 2 away from the z-axis, pi over 4 angle from the positive x-axis, and then 1 up. Okay, 1 pi 3, where's that? Closer in. There's 1. Pi is where? Negative x-axis. Like that. And then z equals 3. Off the screen. That's something like 1 pi 3 back there. 3, 7 pi over 4. Where's 7 pi over 4? Yeah, half, that's like splits the fourth quadrant, right? Something like that. And then z equals -1. So down here. Let me just barely touch the chord and it goes. All right. Okay, what is r equals 4? So that's a set of points. What set of points is r equals 4? Did you come up with that? Okay, so people are saying circular cylinder. Good. Why is it called cylindrical coordinates? Why is it called cylindrical coordinates? Because a constant r value gives you a cylinder with its axis, the z-axis, right? This is why it's called cylindrical coordinates. Because a constant r value gives you a cylinder. Right? Z equals 2 is what? Same z equals 2 it's always been. Horizontal plane. It's every point that has a z equals 2 coordinate. Right? Theta equals 5 pi over 6. What is that? Is that a plane? Kinda. Kind of a plane. Why is it? Why do we have to qualify? That's not exactly like what we think of as a plane. Yeah, so maybe we call it like a half plane or something like this. It's got an edge, right? It doesn't extend everywhere in all directions. So what's your turn? Sometimes it does, sometimes it doesn't. I'm trying to get it to turn. It's not turning. But anyway, so it's basically it has an edge. If it's an angle 5 pi over 6, so it's going to start at the z-axis and just extend out in that direction. But it's going to for all z's and all r's, right? For all z's and all r's. In that 5 pi over 6, almost halfway around. So it's been kind of like what you might think of it like a half plane. But that's going to keep going in that direction. The direction of 5 pi over 6 just extends forever. So I'm showing a curved edge on it, but it's going to have an edge at the z-axis, but this is going to go on for all z values out for all r values in the direction of 5, 5, or 6. Okay, does that make sense? Yes, please.
Do all our values have to be positive?
They don't have to be, but I think also usually they are. Usually I don't see. I rarely see, like when you're dealing with polar coordinates, you'll see negative values of r. I don't see them when you're doing cylindrical coordinates. Typically, theta is from 0 to 2 pi, and r stays positive. Other questions? Okay, so let's try a harder problem here. So the hard part about this is imagining and sketching the solid. But we need some more challenge today. It's been easy so far. So we're going to set the triple integral in cylindrical coordinates to integrate some function, r, that's our theta and z. And here's the solid E. Outside of x squared plus y squared plus z squared equals 1. Inside of x squared plus y squared equals 9. Below z equals x squared plus y squared plus 3. Above z equals 0 and confined to negative x less than or equal to y less than or equal to x. So our goal is to try to sketch this as best we can, at least imagine, sketch good enough so we can imagine exactly what it is. Once we get the sketch, that's the hard part. The easier part is then setting up the limits for the triple integral. Oh, so let's just mention that. Triple integral and cylindrical coordinates is going to be f r theta z. What will our limits of integration be? Yeah, so normally we'll do z first. Normally we'll go like bottom to top, and then r theta. And what happens to the r? Joins, multiplies in with the function. So then so it's like a type A polar, right? So cylindrical triple integral is like a type A and then polar double integral. Okay. See if we can get this solid. Okay. That will take some time. Okay, so what does it mean? Are we good? Is this so far? Is that what you were imagining? Some drawings, some of you guys have good drawings. If it's not, the drawing's not perfect, that's fine, but this is the idea of what you're trying to draw. And then what about this negative x less than or equal to y less than or equal to x? What's that about? So we can just sketch that in the xy plane. So you think about what is y equals x? What is y equals x? That's easy, right? That's just this line. And what is y equals negative x? Well, it's this line, right? So what do we want? All y coordinates less than or equal to x. Where is that? All points with y coordinates less than or equal to x would be like below this line, right? So everything below that line. And then all y coordinates greater than or equal to negative x would be all points above this line. This is like an old pre-algebra problem, right? So we're going way back. So which points have coordinates less than or equal to x and greater than or equal to negative x? Both. You see it? Here. Below the y equals x line, but above the y equals negative x line would be this kind of this right-hand quadrant to the right. Okay, so then what does that mean? Let's find a color that will show up on the video. Let's try sky blue. So then we're going like, that's here and here. So let's try to draw this thing now. So below the purple paraboloid, above the blue sphere, and also above the gray xy plane. And then between here and here, right? So it's going to be dz, then r dr d theta. So the z is bottom to top. What's the bottom of this thing? What's the bottom of this solid? Depends, right? Sometimes it's z equals 0. Sometimes it's the top of the sphere. Okay, so here we go. So sometimes the bottom is 0. And sometimes the bottom is the top of the sphere, which is z equals square root of 1 minus r squared. And then what's the top? What's the top of this thing? The paraboloid, right? And it's always the paraboloid, right? Even depending, regardless of whether the bottom is the sphere or xy plane, the top is always the paraboloid. So that is r squared plus 3. So then our outside double integral depends on whether we're coming off the plane or the sphere. So if the bottom is the plane, then we're looking at this right here. So r goes from 1 to right, going from 1 to 3. And then when you're going from the sphere up, it's 0 to 1 is your r values. So we're looking at the projection into the xy plane to do the outside double integral. And then angle. Yeah, so I told you it's 0 to 2 pi, but we have to use negatives here to get this. So we're going to have to go from negative pi over 4 to pi over 4. And then that's going to be whatever the f is times r dz dr d theta. All right, I'll leave it up if you want to ask me on the way out. Web work due tonight at 7. And then cylindrical coordinates is Wednesday's web work, and you got written homework for Thursday. Yeah.
So the 3, 1, and 1, 0.
So when the bottom is the sphere,
He just said you're going up.
yeah, so from that up to the pink sphere there, up to there. The outside double integral is like this thing projected into the xy plane. For what values in the xy plane do we go from the sphere up? So here, I'll draw that. So if we project this into the xy plane, we get this. This is the projection of this thing into the xy plane. So that pink sphere gets projected like that, and then the cylinder is projected like that, and then here's those y equals negative x, y equals x. So when we go from the sphere up to the paraboloid, that's in here. So that's going to be our outside double integral. It's going to be for that region. And when we go from this xy plane up to the paraboloid, that's this. So when you go from the plane up to the paraboloid, this is your outside double integral. That region. So that's why for the sphere, we went from 0 to 1, negative pi over 4 to pi over 4. And then for the xy planar, z equals 0 up to there, that's over here.
From 1 to 3.
From 1 to 3, yeah, right. Does that make sense?